So we finished Unit 1 last week. Test 1 is out there. If you have it, I'll get that from you today. Otherwise, we can get it tomorrow. I won't answer any questions on Test 1 until we got everybody's in. So, just like on the quizzes, though, we'll be able to do corrections on the test. Like last semester, redo the ones you got wrong. Show your work. Get up to half your points back. If you have any issues trying to redo them, if you're not sure what to do with them, let me know. I'll sit down and work with them with you. Or you can work with a classmate, or you can work with one of our math tutors down in the Academic Support Center. Whatever you need, we'll make sure you get through those. Okay, so today, Unit 2. Unit 2, we're going to cover two things. We're going to cover our machining formulas. Bless you.
Thank you.
This includes two things, cutting speeds and cutting times. Time to complete a cut. Then we're going to look at spur gears. Look at spur gears mainly because they're used in a lot of equipment and a lot of math behind them, a lot of formulas. It's a great application of using formulas. So our first thing today is to look at surface cutting speed. I'm assuming you went through this in your program classes last fall. None of it happens. What surface cutting speed is, it is in one of two applications generally. Turning on a lathe. You have the material that's turning, and you have the tool cutting into the material. It is the speed at which the material goes past the tool. Milling, looking at this now from the top view, now the tool and that looks like a mill. There's a reason I'm a math teacher, not an art teacher. So the tool that's spinning, and the surface cutting speed is the speed again in which now the tool is going past the material. In either of those cases, we have a diameter. Turning situation is the diameter of the material. The milling situation, diameter of the bit. And we have, of course, RPM. And in the case of the turning, it's how many revolutions the material is moving, turning per minute. The milling, it's how many revolutions the mill itself is turning per minute. If our diameter is measured in inches, typically is in both cases. Surface cutting speed. Again, that is simply the speed at which the tool, the surface of the material are passing each other, whether it's the tool that's moving or the material that's moving. It's going to be given for cutting speed, and this is going to be in feet per minute, is given as pi times the diameter. Well, what does that calculate? Well, you're thinking pi over 4. Sorry, pi over 12. Pi times diameter is diameter of the tool or the diameter of the material, whichever one is our object here. Or not diameter, circumference. Pi times diameter circumference of that circle. Times n. N is our RPM. Over 12. Why is it over 12? Yeah. Diameter is in inches. Cutting speed is in feet per minute. So dividing by 12 is to convert it from inches into feet. The RPM is already per minute, so that gives us our per minute status. So this up here, pi times diameter is the circumference, times RPM, that's the total difference traveled. That's the number of circumferences that go through in a single minute. So if we have 2.5 inch piece of material on a lathe at 400 RPM. A surface cutting speed, pi times 2.5 times 400, 12. Actually use 3.14 per pi times 2.5 times 400 divided by 12. 261.67 per minute. So again, that is that speed between the tool and the surface of the material. I can do a similar calculation for 1/4 inch end mill. RPM. Surface cutting speed will be pi times 3/4 times 600 over 12. But I don't divide, I get a 117.75. Second. Now, occasionally, you want to double check your setup to see what the surface cutting speed is. Most of the time, however, going the other direction. Know what you want your surface cutting speed to be. Did he define how many RPMs you should run the machine at, whether it's still setting the lathe or the mill? You need to set the RPM for the machine. C equals pi dn over 12. Now I realize you guys use diameter times RPM over 3.82. 12 divided by pi is 3.82 is where that comes from. That's all they're doing is dividing out the 12 divided by 3.14. You can see. That's all they're doing. That's where that number comes from. It's a little bit of a simplified formula. It does work every time. It's just easier to remember this formula because I know pi times diameter is the circumference, times n is your RPM, that's your total distance traveled. Anyway, we want to solve this for n. We did a little bit of this in the fall. I'm solving these formulas for a given variable. If I want to solve this for n, first thing I have to do is I'm going to multiply by 12 to get rid of the 12. So I now have 12c pi times d times n. N by itself, it's multiplied by pi and d, so I'm going to divide by pi and d. 12c over pi times d n. That's our formula for RPM. I realize you have RPM equals 3.82 c over d. Use that, that's fine. It's going to come up to exactly the same. So here, let's say that we are turning stainless steel carbide cutting tool. So I gave you guys that packet last week with our formulas in. Didn't get one, I do have extra ones up there. I can get you, grab you another one if you need to. On page 241 of that packet, there's a table. Now this table is your types of steel that you're cutting. Your material that you're cutting is on the, not types of steel, it's the material. It has aluminum and annealed brass and stuff on there as well. Depending on whether you're turning, milling, drilling, or reaming, what type of tool you're using. Now for tooling, I realize you guys use mostly Ceramed inserts now. This lists high-speed cutting tools, high-speed steel cutting tools, and carbide cutting tools. This packet's about 15 years out of date. The speeds are the same. It's just the math is the same. It's just the tooling is different. You have a little bit more advanced tooling with the Ceramed inserts now. Did I ever tell you guys where Ceramed was developed for? When I was in college at UW-Madison, one of the professors I had in one of my engineering classes had actually worked on developing Ceramed. It was developed for military, for body armor and helmets. He showed me, or he showed the class, some of the videos from the testing when they developed the helmets. So they mounted the new Ceramed helmet versus the old steel helmets. They mounted the Ceramed helmet on a post, and at 200 yards, they fired a 50 caliber at it, put just a little dent, that big around, maybe that deep in the helmet. So then they went back and they redid it with a crash test dummy with the helmet on, shot it in the head at 200 yards, barely scratched the helmet, took the head clean off the helmet. That's when I realized maybe we were over-engineering the helmet. Take your head clean off, but at least it'll still be pretty.
It did its job.
It did its job.
For a little salt stuff. I don't know what you're complaining about.
That's not a good way to get ahead in life.
Yeah.
Oh, wow.
No pun intended.
Dad jokes.
Yeah.
Had a headache.
Yeah, that leaves a little bit of a mark. So anyway, we're turning stainless. We're using a carbide tool. 200 feet per minute is our maximum speed. We want to stay close to that. So to find our RPM, N is going to equal 12 times 200 divided by pi times D. Let's say we're turning 1.5 inch diameter stainless. When you put this in your calculator, be careful. You do 12 times 200. To divide by that, you're going to put divided by, but you're going to have to put parentheses. 3.14 or pi times 1.5. Then you have to close the parentheses. Bottom of this has to be in parentheses when you enter the calculator, because the calculator has to remember that fraction bar says you got to do everything on bottom before you can divide by it. Put that parentheses to make sure the calculator knows to multiply those first. 509. 509.5 RPM. I'd probably round down to 500 RPM just to. Now, one thing with this chart, if you look at aluminum, those cutting speeds seem to be pretty high. You look at, like, turning with a carbide tool, they're looking at 1,000 to 1,800 feet per second for a surface cutting speed. If you were to just throw a piece of aluminum in a mill and run it at 1,800 feet per second as a cutting speed, what would happen? It would melt the aluminum. That, for aluminum, all the speeds on here for aluminum are assuming you have pressurized lubrication. That is, when you get into this, there's two schools of thought with cutting aluminum. One is you cut it slow so it doesn't melt and gum up your tools. Problem with that is you get more surface tears in it. So the other theory is you go high speeds and you just blast it with coolant to keep the tool clean. Which is better? Richard probably has an opinion on it. I really don't. I haven't worked with it enough to know. I've worked more on the molding, casting side of aluminum than I have on the machining side of it. We're dealing metric. In metric, our surface cutting speed. So pi times diameter times the number of RPMs, but it's over 100. Or pi times diameter times RPMs over 1,000. Reason for this is cutting speed is always in meters per minute. This formula here is if the diameter is given in centimeters. This formula here is if the diameter is in millimeters. 1,000 millimeters. That's all that bottom number is. That's saying there's 1,000 millimeters per meter, so we're converting those millimeters into meters. 100 centimeters. So cutting time. When you guys discuss cutting time, you discuss chip load and all that stuff. We're going to keep it a little bit simpler. We're not going to look at the number of cutting surfaces on the tool. 2-tooth mill versus a 3 or 4, it makes a difference. We're just looking at advancement per revolution. So the time to make a cut, go through the length of the cut, L, divided by F, which is your feed rate. That is that advancement per revolution, times your RPM. So the F times N is going to give you your inches per minute. You're taking your cut in inches and dividing by that. It's basically it's distance divided by speed to give you time. That's all it is. So if you have a tool that has a feed rate 0.03 of an inch per revolution, you are running at 400 RPM, which I realize is along the low side. And you have a cut that is 4 inches. This is more for the mill. You're going to mill a 4-inch groove in a piece of material. Our time required to do that, 4 inches over. So 3 inches per revolution times 400 per minute. So here again, when we calculate this, we have parentheses around the bottom. So it's going to be 4 times parentheses, 0.003 times 400. Close that parentheses. Oops, I should have 4 divided by. Let me try that again. 4 divided by parentheses, 0.003. 100. There we go, 3.33. That is minutes. The only time in this formula is the revolutions per minute, so our time works out to be minutes. Metric version of this is just whatever unit the length of your cut is, has to be the same as your feed rate. Whether it's centimeters per revolution, millimeters per revolution, the length of your cut has to be measured in the same units. Now this can be doubled up with our other formula. Let's say you want to mill 9-inch groove in alloy steel with a 5/8 inch carbon steel end mill. So let's say we look this up, alloy steel, carbide. Carbide tool here. 225 to 450 is the range listed for our allowable surface cutting speed, feet per minute. That's a big range. Usually what you choose depends on what you're looking at. Higher speeds, like I said, can cause more gumming, but it usually causes a little bit smoother surface, a little less tearing. If you get too fast, it causes a lot of surface tearing. There's a sweet spot in there. If this were on a quiz and I asked you to use the table to look up the speed, I would actually use both the low end and the high end, and I would have a range. That would be acceptable as an answer to the quiz. Let's just say we are going to choose, for this purpose, 350 feet per minute is what we want our surface cutting speed. So we're going to find our RPM here. 12 times 350 over pi times 5/8. We have to use parentheses on the bottom here. Pi times 5/8. 2140 is our RPM. So when we run right at max RPM, time of our cut, then this is a 9-inch cut. Let's say we look up, I don't have a table for feed rates. Okay, we're just going to do for our tool, we're going to have a feed rate 1,007 inch per revolution. Our time per cut here is that 9 inches, the length of our cut, divided by the 2,000ths times the 2,140 revolutions per minute. Again, we got to remember to use the parentheses on the bottom. 9 divided by parentheses. 002. Close the parentheses. 2.103 minutes. 2 minutes and 7 seconds is what we're running. What do you think? Not bad? Now tomorrow we're going to look ahead at spur gears. Just going to give you a little bit of a pre-look into it here. Spur gears, one, they bring out my total inability to I'm not going to draw in every tooth. I'm just going to skip over here and draw in a couple. Russ County spur gear. Missing a few teeth. No offense. That's not as much of a thing anymore. That used to be a big deal, is to pick on the Russ County.
No, it still is.
Is it still?
Yeah, I was gonna say.
I try not to do it very often.
We do the same.
I was gonna say we do it all the time. So.
We've talked about the Ladysmith Walmart. It was a little spooky. So what we're dealing with these spur gears, first of all, for two gears to mesh together, distance between their teeth has to be exactly the same. At low speeds, you might get away if they're slightly different, but at high speeds, they're gonna lock up if they're not the same. Pitch is what describes that. But it isn't just distance between teeth. There's actually more to it than that. That's essentially what the pitch is telling us, is how far apart the teeth are. A lot of the things that we are working with, you can see when these teeth come together here, they're not all the way in. This is one gear. Here's its teeth. Here's the gear it's meshing with. You can see that that tooth does not go all the way in to touch the inner portion of the gear. That distance between the tip of the tooth and the hub of the other gear is called clearance. Distance that they penetrate each other. Now I'm going to define inner diameter and outer diameter. Outer diameter of the outside of the teeth, like this. Inner diameter is just the hub here. From the tip of the tooth to the outer diameter. Now the tip of the tooth of the other gear to the outer diameter of that gear. That is called the working depth. In other words, that's how far that tooth penetrates the outer diameter of the other gear. That working depth is a very important dimension, because the distance center to center of the gears. Center of this gear to the center of that gear is equal to the outer diameter of gear A plus the outer diameter of gear B minus that working depth. Working depth is how far the two outer diameters overlap each other. This is not a formula given in your packet, and I don't know why, because to me that's a very important formula. Diameter that is most important is called the pitch diameter. The pitch diameter is between the inner and outer diameter. That pitch diameter is really the effective size of the gear. The pitch diameter of one gear and the pitch diameter of the gear net meshing with it is tangent. That means they touch at just one little point like that. The pitch diameter would go through it halfway through the working depth. Now, that working depth, this circle, here's the outer diameter, right? Our pitch diameter's in here. This is half the working depth here. Half the working depth over here. That's one full working depth off the outer diameter. So the pitch diameter to the outer diameter minus that working depth. screwed up this formula up here, by the way. The one- Distance center to center set, it's the outer diameter divided by 2. It's like technically the outer radius for each of them. The outer radius is not really a thing on your. Well, then for that tooth, got big teeth for some. The distance between the pitch diameter and the outer diameter, distance here, is called the addendum. That's all it's saying. It's from the pitch diameter to the outer diameter. From the pitch diameter, the inner diameter, or the hub, that's called the dedendum. Now you guys, they don't machine as many gears as they used to be a big thing. They machined a lot of gears. Not as common as it used to be, but so the addendum and dedendum are not terms that you're going to use a lot, but they are used for calculating other things. Tomorrow when we come in, we'll look at formulas for these spur gears. I just wanted to get that vocabulary out there so we're ready to go. For right now, working on the cutting speeds, finding the RPMs, and time to make a cut in this packet. Page 242. 1 through 57, the odd or problems on doing that. Again, you don't have to do all of them. Do a couple, skip ahead to the more difficult ones. Make sure you do. They do a pretty good job in this packet of labeling which type of problem it is. Make sure you do a couple of each type. Ones that say complex problems, those are the ones where you have to find the RPMs first and then use that to find the cutting time. Whatever, those are compound problems. We should do a handful of each. As I said, this is a very short unit, which means this Thursday we'll be having a Unit 2 test already. I will actually get that posted out on Blackboard probably by the end of the day tomorrow. So that if you want to look at it and get started on it early, you can. So this, what's that?
I think it already is.
Is it already out there?
Yeah.
Okay. I know I did a lot of stuff last week when, well, you guys were doing your test on Thursday. Test days are kind of my day to catch up on paperwork. So yeah, you can get started on it if you want. This Thursday will be another class like last Thursday. I will log in, but if you guys are doing okay on the test, we'll.
And you put a new quiz or test and it drops our grade.
Yeah, our grade just.
It does because it puts it as zero. The reason I did that, I can set it so that it doesn't, if there's an unmarked grade, it doesn't count it as part of your percent. But a few years ago, I had a student who didn't turn in half his stuff. So I just left it blank. Because if you put it, it's easy when you look at the grade, it's easy to see a blank grade. It's easier than to pick out a zero grade. Well, because his grade was blank, the assignments he did fairly well on. So he had like a B minus. End of the semester, he failed, and he's all pissed off. He's like, Blackboard said I had an 86% or whatever. It's like, yes, but half your grades were missing.
Yeah.
Well, I didn't turn any assignments in the last couple of weeks because I didn't want to lower my grade. Like, really? Do you think that's how it works? Yeah, so I've got it set so as soon as if it's unmarked grade, it counts it as a zero, which does look bad.